Okay, fantastic. Thank you. First of all, good morning. I'm sorry that I couldn't be there in person, and I was hoping to come to Bangalore for this one, but unfortunately, that didn't work out. I really am hoping that you're all having a good conference and enjoying the nice weather in Bangalore. So, first of all, let me thank the organizers for giving me this opportunity to speak. And the title that was given to me is this one, but I've taken a bit of a liberty and slightly changed it to something like this, partly because we have done more work on pulsars than fast transients with this new telescope. And secondly, some of the work that we have been planning to do with the fast transients is especially coming or stemming from the work that we have done for pulsar science in the recent past. Let me just get rid of this hiding button. Right. Oh, sorry. Did I lose that? Okay. Okay. Oh, good. All right. So most of you may have heard about this telescope, but for those who may not have heard, uh, this nice and wonderful telescope we have in outback Western Australia. It's a low frequency interferometer located in Murchison site, which is the same site where SKLO is currently under construction. It operates from 70 to 300 megahertz. It is comprised of 8,192 dipoles arranged in groups of 16, which we call tiles. There are 256 of them. 10 years ago, when the telescope came into operations, we had 128 of them with a maximum baseline of 3 kilometers. The first upgrade, that was 5 years later in the timeline. So that doubled the number of tiles, and so is the maximum baseline. And the second one, which has just about a collecting area which is equivalent to 4 GMRT antennas or something like more like a park's collecting area. But it has a stunningly large field of view, something like several hundred square degrees at the frequency range that we operate. So as an example, on the left, you see the primary beam response at two different pointing, one for the near zenith pointing and the bottom one is for a southern pointing. So that by itself is like an important ingredient to do to make a fantastic transient machine. But in practice, that has been pretty much underutilized, particularly for pulsars and fast transients, mainly because that was not the original science driver for this telescope. It was primarily built as an imaging telescope, and doing a continuum imaging surveys and detecting EOR was the main science scope. But we have been doing a lot of pulsar work. Otherwise, I wouldn't be giving this talk. And the functionality we had is what is called the voltage capture system. And this is a capability where we record channelized voltage data from every single tile. And that's 128 of them. And that's like a lot of data. And that's it. We don't have any backend on site. So if you want to do anything in high time resolution, which is pulsars or something else, you have to bring all this data to the POSI supercomputer, which is about 800 kilometers away. Then that is where you do everything in post processing. So typically, everything that you would do on a real time processing and backend, we had to do it on a supercomputer offline. So we started off with the pulsars, and over the course of time, we also started doing other things like a little bit of work on FRBs, fast transients, and some non-astronomical applications like passive radar. So this just shows like a brief timeline of whatever journey has been. 2015 is when we commissioned this system, but even before that, we did some technology demonstration and did some pulsar science work early on. But pretty much, that VCS coming online was like the dawn of the high time resolution science for the NWA. The most important task we had at hand was making a full coherent beam so that we can get the maximum possible sensitivity. And that kept us busy for doing a lot of interesting pulsar work. And by 2021, when the system was upgraded to phase 3, we had to pretty much revamp all the software subsystems that we had developed. And we had already started some important flagship projects like Smart Survey, which I will describe in a second. And by 2023, we completed the data collection process. So without going into details, the bottom line I want to say is that it has been a pretty great decade of productive science and learning with a lot of publications, and many students have been trained in activities related to high time resolution science with the MWA. So yeah, just a quick overview of the system we had before and after the upgrade in the legacy system. So we were recording the data after two stages of channelization, and there is still voltage time series data. And depending on the science applications, you either convert them into like a full stocks at 100 microsecond, 10 kilohertz. That's good for a lot of pulsar work or even FRB work. And or you just undo the second stage of channelization by doing an inverse PFB. So you can get to like a microsecond time resolution, which is what is good for millisecond pulsar work. In the new system, the big difference is that we tap the signal after one status of channelization, and everything else happens inside the correlator or high time resolution software subsystem. And the first thing that to come online was pretty much like replicating a version of the system we had back then, which we call now smart mode. And then in principle, you can also like implement others. So as of last year, this was pretty much the state of the play. And most recently, we have also like implemented the offline capability to do the correlation, which means you can do things like fast imaging that you need for FRB searches and so on. So I'm just going to give you like a couple of examples of some of the science we have done, and I'm picking up some examples that are synergistically close to like fast transients work. Like for example, looking at single pulse studies of well-known drifting pulsars like a 0034, which shows multiple different drift modes and a lot of nulling, and that was one of the early signs. And also looking at things like giant pulses, and in this case, looking at simultaneously using CRAB and MWA, so you can cover the frequency range all the way from 100 megahertz to several gigahertz, and that was work of Bradley Myers, and both Bradley and Sammy were our first generation PhD students who did a lot of heavy lifting for the early system development. We also have been taking a good advantage of the fact that MWA has an excellent complementarity with other telescopes in the southern sky, especially with the GMRT and the Parkes and now no longer operational Molonglo or at most. GMRT, for example, co-observing pulsars like a 0034 helped us to put some constraints on the emission heights using retardation aberration kind of an analysis. And the right one is a first low frequency detection of an intermittent pulsar that basically made use of a ring buffer mode that was implemented for VCS. In this case, the trigger was actually done manually, but still demonstrates the kind of capabilities that we wanted to achieve in due course of time. And speaking of FRBs, and the most readily accessible data products from MWA, which is an interferometer, is visibilities. Some of the early searches were done using the image domain searches, using 2-second visibilities early on, then eventually using a half-second visibilities. And we did some blind searches, and we also did some shadowing observations when ASCAP got its craft project going. And then, of course, we also looked at archival data from VCS for some repeating FRBs bursts. All of them have been like a pretty much null detections, which is not a hugely big surprise given the amount of time we have spent and the rather uncommonly used frequency band for FRBs or even pulsars in general. But the bottom line to keep takeaway is that if you look at the kind of fluences that are being reported for, say, for example, repeating FRBs, that's the only kind of FRBs detected at 3 with all FRB detections. Other important things about MWA is that it is electronic steering. It's an aperture array. So response time is incredibly small. So in a matter of seconds, you can flew to wherever you want. Again, that is another underutilized capability. And more recently, we have been using it to detect prompt emission from things like long GRBs. And again, that some tantalizing detections with some follow-up, nothing that will make you jump up from the seat, but it turns out to be like possibly some signal from digital TV. But again, the bottom line is that even if you take it as like a non-detection, we can put some interesting constraints on jet and ISM interactions. So it's the kind of capability that will be hopefully used increasingly in the coming decade. That's all about astronomy applications, but MWM has also been like used for like some of the non-astronomical applications. One example is like using it as like a part of a bistatic or multistatic radar network, so that you can detect the signals from FM signals reflected from space debris or satellite or space junk, as you might call it. The reason why we can do it, because we have access to the voltage data, so you can develop like a match filter processing techniques. And that has been pretty much the focus of Brendan Hersey, who did a PhD on this very useful topic. Okay, so I'm moving on to some of the projects that we have been focusing on more recently. So one of them is the SMART survey. That's an all-sky survey that nicely leverages some of the most major strengths that telescope has. The combination of a large field of view and the voltage capture system computational cost. In fact, that's one of the main reasons why we can do such projects. What I want to emphasize is that it's not just another survey. Yes, it is sensitive, more sensitive than some of the pulsar surveys in the southern sky, but it's also a survey with SKA precursor. So it's going to teach us a lot of useful things that we might need in the SKLO era. And it is also going to fill up an important gap that there is no reference survey at the moment in the SKLO's frequency band. And most importantly, that we are recording voltages, not the filter bank or channelized detected data. So that opens the door to multitude of reprocessing options, both now as well as later. I won't go into the details, but there have been like a multiple publications describing the details of our survey design and science goals and pulsar discoveries and so on. Third one in the series has just been published last year. And there have also been like a bunch of publications in the new pulsar discoveries and their follow-ups and the software and techniques that we have developed in the process. And you can go and check them out at your leisure. The important point I want to make is that our big focus was to basically to take this window of opportunity and complete the data collection for the entire sky, which is the sky south of a plus 30 degree. And we have achieved that as of like about a year ago. There is 4 petabytes of data that covers the entire sky. All of it that has been like a thoroughly quality checked. And the summary is what is shown here. The red dots are essentially the pulsar detections, non-pulsar detections as part of our data quality checks. And the stars are essentially the new pulsars discovered from a tiny fraction of the data that have been processed so far. So it's very difficult to not to emphasize the value of a data set like that. That one of the statements made by our director recently is that it represents a unique permanent record of the electromagnetic state of the sky. And I don't think I can say that anything better. And that's exactly the reason why we are able to take on projects like searching for fast transients and other potential projects as the time is moving forward. So coming back to the SMART survey, so we just started the data processing as of around this time last year. One of our big challenges is like a low frequencies. So even when we are talking about the DMs of like a 200, 300, that's like a very large number of DM trials, something like 16,000. We have a very high time and frequency resolution. Our dwell times are something like 4,800 seconds. And the combination of that basically translates to like a pretty significant computational cost. So we are talking about 20 million core hours on Finburn's NT or O star, and even without considering acceleration searches. So we are taking baby steps. At the moment, our focus is to do what we would like to call as a southern cap survey, and which is the skies south of like a minus 45 in declination. And the star symbols are essentially the new pulsars that are trickling out of our processing. So in terms of like the pulsar yield, so again, our big focus is to demonstrate how SKLO should be doing the surveys and to do as much science as possible. In terms of pulsar count, that we are not competing with the FAST or Meerkat because they are the most sensitive telescopes to increase the pulsar population. But the kind of pulsars that we have been discovering have been very interesting from in their own scientific sense. For example, the first pulsar that we discovered turned out to be like a steep spectrum low luminosity objects, and we are finding many more of them. Second one turned out to be like an interesting variable subpulse drifter, and the third one was like another interesting subpulse drifter, which also shows like a quasi-periodicity nulling. I won't go into the details. The main thing I want to emphasize is that unlike most other search pipelines, the things that is very different for MWA searchers is that we start with the terabytes of data, which is our single pointing, 80 terabytes of data. And we need to do like beamforming, where we process like hundreds of data streams at once and produce like a beamform data that can go into our pipeline. So we started off using like a Swinburne's All-Star supercomputer, now beginning to farm this out on other computers like POSI and commercial HPC options like DUG, and also the computing cluster we have access to in NAOC. Other important thing I want to mention is that SMART is also an excellent, the resource for following up and confirmation of the candidates we would find from other kind of searching. For example, MWA has been doing a lot of interesting science to imaging transient search, and you may have heard about this class of objects called long period transients, and the same pipeline has been discovering interesting objects like sporadic emitting pulsars. And here is an example of one such pulsars or candidate that was nicely confirmed in a SMART data set, and we were able to do a lot of interesting in single pulse investigation. Okay, in the last 5 minutes or so, I just want to focus on what we have been doing or what we are trying to do in the context of fast transients, particularly FRBs. And a lot of this work is being done by Christian Di Pietrantonio, one of our PhD students, and also an HPC expert. And like I said, this project is stemming from the fact that the SMART data are recorded as voltages. So that means, that you can correlate them, you can produce visibilities. So you can do things like the fast imaging kind of approach that Mirror Trap or Spotlight or like a real fast has been doing over the past few years. So try and demonstrate well-demonstrated techniques, a strategy, I should say. But the big difference is that at the low frequencies, your dispersion delays are extremely large. So that brings in like interesting computational challenges. So even with something like 100 hours of data, 4 petabytes of voltage data, that's what we wanted to start off with. And what I want to emphasize is that it is still like a non-negligible part of like a on-sky time. So if you equate like a SMART survey, that 100 hours of data translate to something like a more than 100,000 square degree hour. Again, the sensitivity is not fantastic. We are talking about like a tens or a couple of hundreds of Jansky millisecond. And the plot on the right sort of shows like a expected number of FRBs for various populations that you would expect from CHIME or ASCAP or at most kind of FRB populations. The bottom line is that we don't expect very many FRBs, but given the fact that no FRBs have been blindly detected in this frequency band, going from 0 to 1 could be an enormous improvement. I won't go into the details of the implementation and software, but I will point you to some couple of papers that describe all the details. But the crux of the speed up comes from the fact that the entire end-to-end processing pipeline, which is done in imaging, it is all done in such a way that you minimize the IO and you do every single processing starting from like a correlation, imaging, and FRB searching and de-dispersion while the data are actually held in memory. And this has been like a thoroughly benchmarked on multiple different GPU architectures, and it's nicely portable and should be able to be, in principle, used in other kind of telescopes as well, if that is applicable. So what do we do when we have such a thing? So one of the first things that you need to do is like test it and validate it. You heard that brilliantly many times by Scott just a short while ago. So this is a bright pulse from a O950. O950 is like a O329 plus 54 for northern telescopes. Whenever we have a new system, we just go back and point to that telescope. And if you can't see like a bright pulse from O950, that's a matter of concern. But in this case, you can beautifully detect the bright pulses from 150, even without doing de-dispersion. That's what is shown in left panel in the animation. And the right one is a short time series after doing the de-dispersion. The main point I want to emphasize here is that a lot of our gear was basically developed in the imaging side that is customized and needed for something like FRB searching. If you compare to the kind of typical imaging pipeline that popularly used in MWA, which is a pipeline around something called the WS clean, which uses W stacking algorithm, and which does lots of things in the sequential way. And important thing is that FRB searching or de-dispersion, as we all know, is an embarrassingly parallel problems. And using the most modern GPU implementation, you can get a speed up of something like more than 3 orders of magnitude, at least algorithmically. And that's something like the reason why we can do projects like this on smart data. Like I said, that the details are already there in the literature. And as Scott mentioned, that it's always has been our intention and MWA has always been a strong advocate of that right from early on. So how do we stress test it? Our second DC target is the giant pulsars, which are like a bona fide transients in the sky. And we know that the crab pulsars emits like a kilojansky millisecond pulses. And this is a short snapshot of that observation. And you can see that a nice giant pulse about something like a couple of kilojansky milliseconds, beautifully seen in this data set. And as you can see that from the waterfall plot, and the dispersion sweeps are like several seconds. And that's one of the biggest challenges at searching at these frequencies. Those with the eagle eyes might also spot this red dot there. And if you are wondering what it is, and that is a crab pulsar's cousin, which has like a similar DM, but a lot less brighter pulses. And a guesstimate for that in something like about 150 Jansky millisecond. So finally, VCS data rates have almost quadrupled with the new system, a new upgrade, and it is a kind of an operational mode that is simply not sustainable. So at the end of the phase 3 upgrade, this will be replaced with a real-time beamformer, and that's going to open the door for looking at FRB monitoring or triggering on transients, and also doing a lot of interesting parts. So I will just leave you with my summary. So basically, it has been a decade of a lot of fun and interesting science and learning with MWA. And there is a lot of interesting science that will open up with the phase 3 upgrade starting to play an important role. And we have been quite research productive with whatever the limited system we have in the past. Smart survey is our big focus at the moment. Started off with a pulsar searching. And in the meantime, we have also developed the GPU accelerator gear for FRB searches. And that, along with the upcoming beamformer, should put us in a more comfortable space to also start exploring fast transient sky more comfortably. I will leave it there and happy to take any questions.
Thank you, Ramesh, for the exciting talk both on time domain and imaging part. So floor is open for questions and comments. Questions for Ramesh?
Thank you, Ramesh, for a nice talk. And it's nice to see these developments coming up. Just wondering, in the third phase, you're also upgrading the bandwidth, instantaneous bandwidth?
Actually, no. The bandwidth is going to just remain the same, no increase in bandwidth. What is being increased is the sensitivity, because instead of 128 tiles, so now there will be like a flexible options to either use 128 or 256 or 128 just the long baseline, 128 compact. But in terms of bandwidth, it will be basically the same as what was there before. So what is being upgraded is essentially the signal path, the new receivers, new correlators, new voltage capture system, and of course, the same hardware and firmware is repurposed for the beamformer. So bandwidth hasn't changed in that process.
So, sorry, one connected question. How are
Yeah.
you connecting the 256 tiles? They're only if the front end is not upgraded?
Now the front end is upgraded for 256. So at the moment, let me just clarify, we have 16 what we still call RRI receivers. Out of them, one or two of them have been like giving troubles once in a while, but we still have a good fraction of them operational on the ground. And there are the 16 new receivers which have come from Shanghai Observatory, and they do like the standard whatever 32 by 27 oversampled mode. So in principle, it is possible to use them in the critically sampled mode and use all 256. So yes, in the beginning, it will be some sort of a heterogeneous array. Either you have to stick to like a critically sampled mode for all 256, or if you just want like a oversampled, then you just stick to 128.
Thank you, Ramesh.
Yeah, thanks.
Any questions here from the audience here?
Yeah. Hi, Ramesh. Did you discover any of the rotating radio transients from your single pulse search that you were doing?
All right. So look, I should be very honest. We have a single pulse search pipeline implemented. We have tested that, but we haven't basically completed the full chain of like, for example, machine learning classifier to get the kind of the right efficiency that we need for a seamless use of that. So at the moment, we haven't discovered any new rats because we haven't looked for them, but we know that the basic pipeline works. So as we are running through the pipeline, so it is producing a lot of single pulse candidates, but they have not been sifted through. So we have been focusing more on new pulsars and their follow-up and making sure that the processing pipeline works on multiple different clusters like O-star and DUG and others. So yes, it's possible that, some new rats are basically sitting there, but we haven't had a chance to go through all the candidates, mountain of the candidates.
Okay. Any questions from online participants? Maybe Ramesh, I have one question. So this blink versus WS clean, that speed up of 300x or something which you mentioned, that looks very impressive. So maybe like, is it like some kind of algorithmic changes like gridding or something which blink is doing significantly different than WS clean?
Yeah, so the biggest difference comes from the fact that the WS Clean was basically developed as a fast and efficient wide field imaging pipeline, which does everything that you need to get the highest fidelity image, like gridding and deconvolution, all of that, right? So when you are doing snapshot imaging, a lot of that complexity, something which you can actually get by. So that is a one big change in the algorithm. But otherwise, the real change is coming from the fact that we are only doing like a snapshot imaging, and the original WS Clean was actually developed as a CPU plus original. The GPU existed at that time, as opposed to the kind of GPUs that we now have to do everything without getting data out of the memory. So in terms of algorithmic, I don't think there is a new invention there, but in terms of doing the most efficient implementation that you need to make a good enough image for 20 millisecond snapshot, that's what was the original focus was. So I agree. So in some sense, this comparison is not the most ideal, but if someone wants to do that without the Blink pipeline, that is our option. That is why, the comparison was only made with that. But I'm sure that if someone is to try to implement WS Clean for a faster version for fast transient searching, you can do that. But most of the efficiency here actually comes from the GPU acceleration and the modern GPUs.
No. Thanks, Ramesh. Yeah, it makes the point. Yeah. Any further questions for Ramesh?